purpose of today's lab is to find the relationship between the radius of an object's path as it goes around in a circle and the speed of that object as it goes around in the circle. Now, we always phrase a problem in the form of a question, and you can see here it is phrased in the form of a question. For an object moving with uniform circular motion, in other words, constant speed going in a circle, what relationship exists between the radius of the path and its speed? Now, there's all kinds of different relationships that could exist, right? We could have a linear relationship. If it's a linear relationship, then as r goes up, then v goes up. It could be an inverse relationship. If it's an inverse relationship, as r goes up, v goes down. It could be an exponential relationship. So in other words, as r goes up, v goes up even faster. Okay, so it could be all kinds of different relationships. In the end, you're going to find out what that relationship is. Now, for the first time, you're doing a lab this year where you have to identify a hypothesis. A hypothesis is going to be an if-then statement. So if the radius does this, then the speed will do this. Does that make sense? So you're going to basically fill in those blanks. If the radius, if r, then v does what? You're going to have three sets of variables, as we always do, and that's going to include one manipulated variable. That should become pretty obvious to you pretty quickly what that manipulated variable is. You're also going to have one responding variable, and again, that's going to become obvious to you soon what that responding variable is. And then control variables, you're going to have like 100 control variables. I don't expect you to list 100. I expect you to list the 1 or 2 or 3 that are really important, right? It's, you know, in the end, we should keep everything the same other than my manipulated and responding variable, including the temperature of the air and the air pressure and so on, although clearly those aren't going to matter a whole lot, right? So it's not those ones that we're looking for. It's the more important ones, the critical ones that we're looking for. So you're going to identify a few, one or two, depending upon how many really important ones we have of those control variables. Now, I haven't listed the procedure here, but it is on the handout that I gave you a few minutes ago. I'll summarize it right now. What you're going to do is take an apparatus like you see up on the board, or like I have in my hand right now. Consists of a PVC tube, a little, what's like plastic, and there's a string threaded through that PVC tube. You can see that that string is in no way attached to that PVC tube. Got it? This is not like David Copperfield trying to do some kind of magician's trick here. It's not attached, and it won't be attached. Now, on the end of that string, though, is a rubber stopper. You're going to swing that rubber stopper around like this. Except that right now, as I swing it around, I was holding the string with my hand. I'm not going to hold the string with my hand. We can imagine as it stands right now, if I don't hold the string with my hand, the rubber stopper is going to go off in a straight line. Because it's, by Newton's first law, wants to go in a straight line if there is no force acting to cause it to not go in a straight line. So I need to have a mass attached to the bottom of this to keep it from going in a straight line. Listen carefully to what I just said, okay? This is the answer to one of the analysis questions that you're going to deal with later on, okay? I'm going to attach a 200-gram mass onto the end of this, and that 200-gram mass will keep this rubber stopper, as I'm swinging it around, from going off in a straight line. In other words, this 200-gram mass will keep the rubber stopper moving in a circle. Does that make sense? I'm not holding onto the string. The PVC tube isn't holding onto the string. The only thing that's pulling on the string is the 200-gram mass. Does that make sense? All right. So that's the basic apparatus. Now, what you're going to do is create a data table where you have various radiuses, in other words, various distances from the axis of rotation. We've seen that term in a couple of questions, right? This would be the axis of rotation. Okay, you can see that the distance from the axis of rotation of this rubber stopper right now is quite small. Now it's a lot bigger, right? We're going to change that distance from the axis of rotation. What do you call that, by the way? That distance from the axis of rotation? The radius, right. You're going to change that radius. You're going to change it several times. They've got here 1, 2, 3, 4, 5 trials. So maybe make it 0.1 meters or 0.2 meters or whatever the case. I think it says start at 0.2 meters, I think, in the activity. You can check that anyways. It's not a big deal. And then you're going to swing it around. You're going to swing this around 20 times. But what you have to do, and this is a little bit tricky, it takes a little bit of practice to do this, you have to keep that distance through these 20 turns the same. So in other words, if I swing it like this, okay, this looks okay right now, but watch. Look, the R is getting bigger. That's not good. Not within one trial. You want to keep it the same distance. So you have to practice so that you can keep that radius the same through that trial without holding on to this string. That takes a little bit of practice. Okay, it really does. You're going to time, or your partner is going to time how long it takes for 20 revolutions. And then you're going to time how long it takes for 20 revolutions at that radius again. Then you're going to increase the radius to a new value. And you're going to see how long it takes for 20 revolutions for that radius. And then you're going to do it again for that radius. This is your data table. And the sheet that you have handed out to you, it says data at the bottom. That's not data. Most of that table is, what would you call that table, most of it? Analysis, because it involves calculations. Okay, this is data. This is what you're going to record as you do your experiment today, and then you're going to create an analysis table that looks like this table, or the table that's at the bottom of page 1 in the handout that I just gave you. It's okay to repeat the data in the analysis table, but you should have the data separate from that as well. So under the data heading, you should see this. Under the analysis heading, you should see this, where it doesn't have to have the data repeated. You can have the data repeated, but in addition to that, you've got these 3 columns. Now, where are we going to get the information for these 3 last columns, the analysis columns, the average time? Well, this should be easy, right? The average time is just, sorry? Yeah, it's the mean of the 2, which is add them up and divide by 2. So if I got, let's say, 17 seconds, and I got 17.5 seconds, then the average time would be 17.25 seconds. Good? Let's call this, tell you what, let's label these. Let's call this column A, B, C, D, E, and F. The average time would be B plus C divided by 2. Agree? Okay, how do you find the period now? The period is column E, and that's going to be, no, easier than that. How do you find the period? What is it? 20 seconds? No. It's the time per revolution, right? So we're going to say it's column D, or the average time, divided by 20. The time per revolution. So whatever you get for column D times or divided by 20. Now column F, this is going to be 2 pi r, speed is 2 pi r divided by t, right? Which means that you're going to say column F is going to be 2 times pi times r. The radius is A divided by the period, which is column E. Does that make some sense, guys? Okay, that doesn't make sense, then make sure you ask me a question on that, all right? Nowhere are you going to use in this lab, listen carefully again, because some people will do this, and I know some people will do this, don't be that person. Nowhere in this lab will you use the equation F is equal to mv squared over r. Why not? Because you're trying to find a relationship between r and v. If you're trying to find a relationship between r and v, you can't use an equation that assumes that relationship. Got it? Nowhere. There's a question later on where you're going to want to use it. Nowhere in this lab are you going to use the equation F is equal to mv squared over r. 2 pi r over t, absolutely fine. Now, there's a bunch of analysis questions that you see at the bottom there. I've got 2 of them circled and only 2 of them circled. That doesn't mean that you'll only have to do those 2. It just means that the other ones you will have taken care of already. When you've filled in your table and you've filled in your variables, when you've done what I've said to do already, you'll have answered questions 1 to 4 already. So you don't need to go and do those again. because you'll already have done them. Does that make sense? Question 5 and 6, you will not have done already. So questions 5 and 6, I want you to explicitly do after you've created your table. Identify the force that acts as a centripetal force and determine its value. And then plot a graph of velocity versus radius. There is a typo there, actually. It's not velocity versus radius. What should it be? It should be speed versus radius, not velocity versus radius. Because the velocity is not only changing magnitude, but also changing direction, whereas speed only has a magnitude change, and we can plot that on the graph. So plot a graph of speed versus radius, and then reminding you here to plot the manipulated variable on the horizontal axis and the responding variable on the vertical axis. Tell me, no, don't tell me right now, because you had to identify that, okay, manipulated and responding variable. You can figure that out based on the table and based on the procedure, which variable goes on which axis. Now, your conclusion. What was the problem? What was the relationship between radius and speed? Your hypothesis was if r does this, then then v does that. Your conclusion now, because you had a hypothesis time, you want to relate it not to the problem, but to the hypothesis. Like, ultimately, conclusions go back to problems. But when we have a hypothesis, the hypothesis is based on a problem. So what we're going to do is try to identify whether a hypothesis has been proven correct or not. You're going to restate your hypothesis in your conclusion. If I could spell hypothesis. There we go. That's better. Restate your hypothesis. If R does this, then V does this, and then you're going to accept or reject your hypothesis. I accept my hypothesis. I reject my hypothesis because, well, why do you accept your hypothesis? Why do you accept that as R goes up, V goes up? Or why do you reject that as R goes up, V goes up or goes down? Whatever the case may be. I'll tell you what, your justification for any conclusion should be based on your analysis. If it's not based on your analysis, then what the heck did you do your analysis for, right? What was the crux of your analysis? It's the graph. Go back to your graph. You're going to accept or reject your hypothesis based on what you get in your graph. All right? So restate it, accept or reject it, and then tell me why you accept or reject your hypothesis. Finally, what comes last? Sources of error. Remember, you want to list 2 or 3, preferably 3 good sources of error, but then include suggestions for improvement. There will be ample opportunity to find sources of error in this lab. This lab is not a highly precise lab. Although you should get decent results, it's not highly precise. Again, there's lots of room to find sources of error in this. If you find a source of error as you're performing the lab, you can fix it then and still use it as a source of error. You don't have to say, I'm not going to fix it because then I'm going to take away my source of error. No. You can. I'd rather you fix it as you're doing it rather than next time, right? So keep in mind as you're going through the lab, oh, geez, this could be better. And write that down. If you find something that isn't great, to do with the procedure or do the apparatus or whatever the case may be, write that down. Write it down as an idea. And then I try to identify a way to make it better. And then when you go to write this up, due on Tuesday, so when you go to write this up Sunday or Monday, you're not going to be like, geez, I don't really remember. Like, what were some of the sources of error? I don't remember. Okay? Try to identify those today. Does that make sense? All right, so what do you got to hand in for this? It outlines this on Google Classroom in the assignment. It says you got to hand in your problem, your variables, okay, your hypothesis, your data, your analysis, your conclusion, sources of error. What is conspicuously absent from this? 2 things. What do you not have to hand in for this? materials, you do not have to list the materials, and the procedure. You do not have to list the procedure. Now, the reason you don't have to list the materials and procedure for this is because the handout that I gave you already lists them. So it would just be a matter of retyping it, which is, I think, a waste of your time. Now, it does list, I did give you the problem as well, but the reason that I want you to state the problem is because it's pretty hard for you to do a hypothesis if you don't actually have a problem there, right? So even though I gave you the problem, and you're not really getting marked on the problem because I gave it to you, we need it there so that we can make a reasonable hypothesis.